So on Monday, we have talked about how to estimate the parameters in different equations from the real data. So I have show you what the different equation is and one applications in the predictor pre-systems in biology. And so we have talked about the challenging problems, and then we talk about the second applications in estimating gene regulation networks. And so we talk about the feed-forward loop, which is the most popular patterns inside this network. And so this feed-forward loop is composed with 3 genes. And gene X regulates both gene Y and gene Z, and gene Y regulates gene Z. And all 3 of them self-regulated. Okay, so based on this, and we come with 2 different equations. And so here, YOT and ZOT are the expression of gene Y and gene Z. And here, fx is the regulation function. So it will have either increasing function of x or decreasing function of x. If x is activator, then f is the increasing function of x. If x is a repressor, then the regulation function f function is a decreasing function of x. So we have 7 parameters to estimate based on this model. So the questions, we have 2 questions we want to address for this project. So first, suppose we know the type of regulations between the 3 genes. In other words, we know the regulation will be activation or repression. So in other words, we will know the form of this regulation function. So how can we estimate these parameters from the gene expression data? And we know these parameters have these biological interpretations. So for example, like this alpha y will be the self-regulation rate of y to itself, and beta y will be the regulation rate of the gene X on the y. So this is the first question. The second question is if we don't know the type of regulations, so how can we infer the type of regulation between these 3 genes? So this is the 2 questions we want to address. So this is the gene expression data. So this data is the normalized gene expression data for these 3 genes, and so because of doing the normalization, in other words, they make the mean equal to 0, and the standard deviation over all the gene expression equal to 1. Therefore, there's a negative values for the xt, yt, and zt. Don't get surprised, because this is after the gene expression. And so we identified 3 genes. We choose 3 genes X, Y, Z from thousands of genes. I believe this is for the yeast. Okay, so so we have some measurements on this gene expression over multiple time points. So in this case, we have 8 time points for each gene expression, and so now we can estimate these parameters from the data with standard errors. So this is then we solve the different equations. With these estimated parameter values, and this is the fit, how the ODE solution fit to the data. So the second question is to infer the type of regulations between the genes. So this is like doing the model selection, right? If you think about like so basically, if we have the regulation type of regulation to be activation or repression, basically we are choosing between two models, right? So this is exactly like a model selection problems. So a simple way to doing the model selection is that so we can choose different type of regulations on between these genes, and then we will have different OD models, right? And then based on the same OD models, we can estimate the OD parameters, and after getting the OD parameters, we can get the fit of the OD solution to the data. So this is the SSE looks like, and then we can compare with other type of regulation and to see which one has the smallest sum square errors. Okay, so this is the infer for the type of regulation between genes, and so the challenging for this application is that the data are very sparse. So for this case here, we only have 8 time points, and not accurate. So so for this gene expression, this is a microarray data, and so if you're familiar with microarray data, and these are not accurate at all for the measure the gene expression, and now they have more accurate technique available to measure the gene expression. And also we need to require to do the model selection. So this is the application in genetics. So now let's look at another application in pharmacokinetics. So pharmacokinetics, how many of you have heard about the pharmacokinetics term? Can you raise your hand? Okay, okay. That's not surprising. I didn't know this term before either. Okay, so pharmacokinetics basically is to study the dynamic system of when we take the drugs and to see how the drugs distributed over our body, we absorb in our body as well. So basically, for each type of drugs, before they commercialize these drugs, they need to do this pharmacokinetics analysis and to find out kind of the absorption rate, distribution rate, this kind of key characters for these drugs. And so this is a kind of very big areas in pharmacology. So here we look at one applications. This is called HIV combination therapy. So basically, this is a treatment on the HIV for subject with HIV virus. So there's two treatments. I guess there's two type of drugs. One is IDV, the other is RTV. Okay, so they have two different combinations. Okay, for these two type of drugs, and so here we call it treatment 1, treatment 2 here. So after the patients taking these drugs, and then we can measure the concentration of these two drugs inside their blood at multiple time points. So this is the time points with the measurements. So you can see not equally spaced. Okay, this is measurements for 16 healthy volunteers after they taking the dosage twice daily for 2 weeks. And so this is the concentration of one drug in their blood. Okay, so you can see here. So for this is for 16 subjects. So you can see here all the drug concentration has similar patterns. So basically, it's increasing at the beginning, right? When they first take the drugs, the concentration is increasing in their blood, and after certain times, their body is going to consume these drugs, and the concentration of the drugs in the blood is going to decreasing. Okay, so this is the patterns for the drug concentration in the blood. Okay, so there's a popular differential equations in pharmacokinetics to describe this change about this drug concentration. So here, for this equation, Ci of t stands for the drug concentration in the blood, and Cl is the rate of the totally body drug clearance. Ka stands for the drug absorption rate, and Ke stands for the drug elimination rate. And here we have the I is for the index of the patients. Okay, so basically, we can imagine for each subject, they will have their own drug absorption rate and drug elimination rate, right? Really depend on their body reaction to these drugs. And so in other words, every subject will have their own value for the Ka and Ke, these parameter values, right? And at the same time, these parameters must have some like similar, right? Because they're taking the same drugs. Okay. So in other words, this Ke here will have some like a population values, the value of these parameters in the population level. There will be also the individual levels of these parameter values for individual subjects. So this is in statistics, we call this as a mixed effect model, right? So basically, we will have a fixed effect, which is the values of these parameters on the population level, and we also have the random effects, which is the departure of these parameter values for each individuals from the population level. Okay, so this is mixed effect models, and so because this Ci is a solution of this ODE, the Ci of t here, the drug concentration is actually a nonlinear function of t. This is a nonlinear mixed effect models. Okay. So here, so this is kind of to show you some results. So here we have these three parameters, Ke, Ka, and Cl, and so here Pe stands for the point estimation, Se stands for the standard error estimation. So this is to show the values of these three parameters in a population level. Okay, and so this is to show the ratio between the treatment 2 to treatment 1 in the population level. And at the same time, we can calculate the standard error, the variance of this random effect Ka and Cl in the data. So this is a mixed effect models. So after we estimate these parameters, we can look at how the ODE fit the data, and so this is the ODE solution fitted to the data for the 16 subjects. So each subject will have different values for the ODE parameters, and they will have their own solution. So the unique character for this application is that we have repeated measurements for one dynamic process. Like for this drug concentration change, we have these measurements on 16 subjects. Therefore, we include the fixed effect and the random effect for these ODE parameters. So this is the third applications we are working on. So So we have learned these three applications in biology, genetics, and pharmacokinetics. So there are many other applications when we need to estimate the parameters in the different equations. I choose these three because it is a unique aspect on this application in terms of the statistical models we are working on. So so now I'm going to talk about some general methods on how can we estimate the parameters in the different equations. Any questions so far? Is this good? Okay. Oh, yes. So this is actually the talk I gave like 5 years ago. So this is my daughter, when she was 2. So that's she's 10 now. So 8 years passed. It's going very fast. Okay. Yes. So I have 3 kids now. Okay. So so now let's talk about the methods for the estimating parameters in the different equations. Okay. So let's first talk about the first methods. It's also the classical methods we use, and also the most popular method used to estimating parameters in the different equations. Okay, so the idea is the follows. So when we talk about challenging in estimating ODE parameters, the challenge is that most ODEs do not have analytical solution, right? This is the most challenging part. In other words, we know the x of t will satisfy this ODE model, but we actually cannot write down exactly the form of x as a function of t, right? That's the problem. Okay, so what can we do? So we have learned that we have numerical methods. So if we know the values of the ODE parameter beta and also the initial conditions x0, which is the value of x at the starting time point, we can solve the ODEs numerically, right? Yes, there's many nice numerical methods available, and actually can solve the ODE pretty accurately. So what we can do is that so our goal is to find the ODE parameters such that the ODE solution will fit the data the best, right? This is our goal. So what we can do is that we can search the candidate values for the beta and x0. Then we can solve the ODEs with these parameter values beta and x0, and we got the solution. And then we can look at how far the solution to the data, right? We calculated the summation of the square of this fit, right? These residues. So you can imagine if we search for many candidates on these parameters in certain ways, we will find out the optimal values for this beta x0, right? Yes. So this is definitely a good standard we can use. There's no better standard because this is our objective. We want to find the ODE solution that fits the data the best, right? Okay. So this is actually in statistics we also call this as a nonlinear regression. The reason is that here for the function x, it is a nonlinear function of t, right? Okay. So this is so in other words, there will be no closed formula for the beta here because there's no it's not a linear function of beta. Okay. So this is the nonlinear least squared problems. So the problem for this method is that so we have learned that the ODE solution are very sensitive to the parameters. So then you can imagine a small value of the beta, it will result a big change on the x. Okay. So therefore, when you search for the optimal values, you will find out in your optimization surface, actually there's many multiple mode available. So it's hard to I didn't include in these slides. There are many local mode. Okay, so it's hard to find out the optimal values. Secondly, when you solve the ODEs repeatedly, if you solve ODE just once, it is pretty quick, less than 1 minute. But if you can imagine, because it's so hard to find the optimal value for the beta and x0, actually we have to search for thousands of candidates. In that case, the computation will be very intensive. Just to give you one ideas, I heard there's one biological lab. They want to find the optimal value for their OD models, and it took them 1 year to run 2 computers to search for the optimal values. So it's a very intensive process. And also another problem for this method is that they need to estimate the starting values x0, right? And so if you think about if you have 4 variables like our predictor pre-ODE system, if you have 4 variables, then you will have 4 starting values, initial conditions for these 4 variables. So in other words, your parameter space is increasing, right? Yes, this is another potential problems. This is the first method. The second method is called the 2-step procedure. So this procedure has been studied by Ramsey and Silman in 2005 in our functional data analysis book, and also in Chen and Wu's 2008 paper. And there's some following work as well on this 2-step procedure. And so the idea is the follows. So here, we want to find the ODE parameters beta that the X will fit the data as better as possible, right? So the problem here, so if you look at this, the ODE models, okay, basically the unique about the ODE model is that the left side is the derivative of X with back to T, right? In other words, this is if we treat this as a response, right? And if we treat the X as a covariate, this is a classic regression problem, right? The only problem here is that we actually don't know the second derivative, right? That's the main problem. And so what we can do is that actually in our beginning of our course, we have learned that so here we have some discrete measurements on the X of T, right? We know that we can use the smoothing spline method, for example, right, to estimate the X directly from the discrete data X or the Y, right? So we can estimate X, and at the same time we can also estimate the derivative xt, right? So to remember, the derivative of x of t will be equal to the linear combination of the derivative of the basic functions, right? Actually, there's no cost to estimate the derivative when you got the x of t. So then, after we know the derivative, then we can treat the derivative as the response, right? And then we can treat the x as the covariate. And then we can treat this ODE as a regression problems, right? And we try to minimize the left side to the right side and to get the estimation for the beta, right? Okay. So this is the second step. So after we estimate the derivative, we can estimate the beta by treating this as a regression problems. We can doing the using the least squares. Okay. So the advantage for this method is that so you can see in the whole procedure, actually we don't need to solve the ODE numerically, right? So so you can just estimate the x of t and the derivative of x of t directly from the data, and then you can do the regression, right? So so the computation is extremely fast, okay? And also we don't need to adding the initial conditions as extra parameters, because here we actually don't need the don't need to solve the ODEs, so therefore we don't need to specify the initial condition for the ODE model, right? So this is another advantage. Of course, this method also have its disadvantage. What's the disadvantage for this method? So we have learned that because there's no direct measurement on the derivative, so generally when we do this non-parametric smoothing, we find that we can estimate the x with an accurate estimation. But when we estimate the derivative, the estimation error will be increased quickly, especially when the data are sparse. Okay, so it is hard to get the accurate estimation on the derivative. So if the estimation on the derivative has a large errors, you can imagine if the response has a large errors, it is very hard to get a good estimation on the beta, right? Okay, so this is the disadvantage for this two-step procedure. So it's hard to estimate the derivative accurately. This is the one major disadvantage for this method. Another major disadvantage for this method is that you can see here, when we want to do this two-step procedure, the first step we need to do is that we need to estimate the derivative x of t with back to t using the non-parametric smoothing method, right? So we can do this using smoothing splines if we have the discrete data, right? The problem is that here I will show you the predictor pre system, right? So do remember in that system, it actually have 4 components: the concentration of nitrogen, concentration of the algae, and concentration of the rotifer, and concentration of the reproducing rotifer, right? So, but in the lab, we cannot measure the concentration of nitrogen and the concentration of the female rotifer. So, in other words, there are 2 variables do not have data. Okay, so in this case, it is impossible to estimate the N of T and the C of T, the concentration curve, for the nitrogen and for the female rotifer, right? So in this case, we cannot do the two-step procedure, right? Because there's no data for some key variables in the system. So actually, this is very common in the dynamic systems. So in many dynamic systems, some variables actually do not have observations, cannot have measurements. Okay, so in that case, the two-step procedure will not work. So so there's also many several Monte Carlo methods available to estimate the ODE parameters. So the early ones are the MCMC methods. So basically, they will give the prior on the ODE models, ODE parameters, and then they will come with the posterior on the ODE parameters. Of course, there's no closed formula on this posterior distribution, then they will do the MCMC to do the sampling. Okay, and so this is the first method we can use. The second method we can use is the smooth functional temporal method. So basically, they try to address when we do the sampling, the ODE models will have multiple modes, right? So when you do the MCMC, it is easy to stack in the mode, and then you cannot skip out. So this is smooth functional temporary method. They try to skip between multiple modes. And there's another method called Riemann manifold Lagrangian and Hamiltonian Monte Carlo methods. And so their ideas is to using the gradients to help you to search for the optimal ODE models, and they have a fast convergence than the MCMC method. Okay, so these are some popular Monte Carlo method used to estimate ODE parameters. So the general disadvantage for this method is that because of the ODE has multiple modes, so the sampling sequence is not easy to converge, and also this method requires to solve the ODEs repeatedly. Every time when you sampling one new ODE parameters, you need to solve the ODE numerically once. So the computation is pretty intensive as well. And also because they involve the solving ODEs, so they need to estimate the initial conditions x0, which is the actual parameters in the problem. And also we find it hard to program actually. Although the idea is pretty simple, but when you do the programming and you're doing the tuning to make the sampling sequence to converge, it's not easy. Okay, so this is the problem for the Bayesian methods. Okay, so let's have a 10 minutes break, and then we will continue, and I will talk about my favorite methods to estimate the ODEs after the break. Okay, thank you.